Thank you for having me and inviting me here today. I was listening to all the sessions since this morning, and starting off with Vint. I'm sure all of our attendees are Vint. I'm tired of hearing that name, but he is indeed the father of the internet. And I was reading in the chat some of the comments with that we had. There was like, oh, in such a short time, we have an explosion of social engineering, and we also have a massive amount of learning materials that are available to us. All we have to do is do an internet search. And these two byproducts that we have from the internet is actually what I'm going to do here today. I'm actually going to utilize them because I am doing social engineering through this venue. And I will be hoping to impart some knowledge to you on what simulation tools have to do with sustainability. So maybe it's June. So time that I've lost track of time, as you heard from Nancy before, right? Was it a month and a half ago? We had the Earth Day, and so that was April 22nd. And in support of Earth Day, what my company did was we initiated on a mini series of how we and our customers are going to help this effort to rescue the earth, sustainability, how we're going to use technologies to save our planet. And here I just have a screenshot. If you go to, if you do an internet search on Ansys and Earth Rescue, you'll see this. And so you'll see we have several different, there's a trailer there. And right now we have the first of the series that came out. And the first of the series happened to be power. And so that's very coincidental and convenient for me because here we are with an IEEE-HKN presentation, and we need to talk about power because anything we really look at starts with energy. And of course, Vint did say everything rolls around software, but in order to start coding and writing software, you either need a light bulb or you need power to your laptop or whatever you and something electric that you're using. So yes, we need software, but we also need power. So with power, we use that, just plug in everyday things. I'm talking power for industry, going to work. And I'm not going to limit that to the Earth environment, but we can do it for flight and even in space. So my concern with sustainability is how much energy are we really consuming? Again, if I Google it and here's the link to where I got this information. This is almost current data. In most of the world, this is how many millions of tons of energy we're using. They didn't have a unit scale over here, but it's millions of tons of oil equivalent. So we consume a lot of energy. And currently, most of the energy is provided by fossil fuels, right? From oil and petroleum. And so we're using up a lot of Earth's natural resources so that we can make it into energy. So then we can pollute the environment and then we could destroy the Earth. And we don't want to do that. That's just not a good thing. But if we look at the statistics and we say, so what is the current state of affairs here? And again, another internet search, and let me take a look at the graphs, what they're saying. And they say throughout the years and even into the future, there was a future out to 2050, we are going to still use petroleum. The key takeaway is that petroleum and natural gas are going to remain the most commonly used source of energy, and not the renewables. Not the renewables down here. It may be hard to read the color coding here, but some of these are renewables. So in this day and age of technology, we're still not using renewables. And if I were to look at a map, and if I could take all those electrons that I have in the in quantum computing, again, from the presentations this morning, and I were to look at a map of how much electricity we're using, and say, for instance, these are roads and this is a building, and the colors are, we're really using a lot of energy in the buildings here, and these are automobiles or lights or whatever, but this is how much energy that we could use. And if it were at night and I had the buildings all lit up and I'm using a lot of energy, I'd say, what a waste. Besides the fact that I don't want to pay that electric bill, it's just wasting energy into the atmosphere. So a solution to this problem would be a smart motor. Why do I say smart motor? Because something to recognize are sensors that say, hey, no one's here, right? Let me turn off the switch. Let me turn off the power. Right? Maybe I don't have to make it really cold and use the air, or maybe I don't have to make it really warm and heat up the house. Let me just keep it at some ambient, but if there's no one, if the room is too full, let me just, adjust it accordingly. So we need these sensors, these smart motors, and we need the technology to drive that, in addition to us using less energy or consuming less energy. And that's what the word sustainability is. And that's the meaning that we're trying to get to. And there are folks out there, like, again, another Google search that I do, I looked up climate fighting electric motors. And here I come with, and I just put a couple of bullets from this company, again, just on an internet search to see if people are out there. So people are indeed trying to make these smart sensors. Right. This one happened to be for, for industrial applications. How do I, make the turbines on this machine more efficient? How do I produce more energy from the motor without wasting it? We just heard on the presentation before, it just so happens, this presentation was on aircrafts. Well, how can we make these aircrafts more efficient? Again, airplanes, they consume a lot of energy and they also emit a lot of carbon into the atmosphere. So this is something we want to make sure that we're not doing. So I'm sure that, Textron is looking at these things as well. And if I were, again, looking how to design a really efficient electric motor, and I'm saying, I just showed you that graph where the renewables are not popular, right? We're still dependent on oils and natural gases. Why is that? And that's because I don't want to lose sight of one thing. We can make the best engineered product there is. But what the driving factor really is the amount of time to develop it and the cost to manufacture it. So if we can't make it cost effective, we can't sell it, so we're not going to go forward in that technology. So even though we can master the engineering behind it, it still has to be at a, at a cost that is not as disruptive. And even if we design it and we make it cost effective and we have a very popular product, does not mean that there is success without any failure, right? Recently, just this past month, there was that big article about all the electric vehicle batteries that were catching on fire. The houses were on fire. And I think just like, during the holidays in the US on Memorial Day weekend, an aircraft was caught on fire. Someone put their battery in the luggage cabin and it caught fire. So without fail, as best the technology is, we still have failure. And that's what engineering is. Why are these things failing, right? And why are they failing? Well, we heard the word digital twin before. Well, the digital twin is, let us go and simulate these products and simulate them in the environment that they'll be working in. Okay, whether it's, operating temperature, you know, maybe those electric bikes were, overused and the batteries got really hot and they were in you know, in the deserts of Arizona. So they got really hot, they overheated. Or maybe while they were in that aircraft, in that airplane, in the luggage compartment, even though it's cold, maybe the vibration of it was a little bit too much. So even though we thought we had a great electrical design, we need to also say, what's the operating environment? What's the temperature? What's the vibration? So I'm not just electrical anymore, just like we were saying before. I may have went to school for electrical engineering, but I need to consider, you know, environmental. I need to consider structural. I need to consider, aerodynamics. So we learn as we go on, and we learn enough intelligently to be able to engineer that product. Now, one of the base things in the that the one company was doing, I showed this picture. This is an electric motor. And there is nothing new about this technology or the driving equations for it for almost 100 years plus, almost 200 years. So those equations, so many of you are students. They may have already graduated or just finished your semester. So if you took an electric motors class, power gen, and you heard the word stators and rotors, part of the electric machines, right? Electric motors. But you know what? Those design equations are old. And maybe that's good. Or maybe that's bad, right? When those equations were created, they didn't take into consideration how they were being used. Okay, so they were typically designed what I call a single physics, right? They were just considering the electrical characteristics of it at a very specific temperature. Well, maybe we should now consider really enforcing that our digital twins are utilizing multi-physics, more than one physics. Maybe I should couple my electrical engineering with my mechanical engineering with my thermal engineering. So this way I can help simulate and predict the operation of this device when I am designing it. So before we get those failures, and I just realized I was moving around my mouse without the highlighter on. Let me see. Just let me make sure I have this here, my laser pointer. Much better. So when I was circling before and I thought I was doing something, I wasn't. Okay, so we were trying to talk about this electric motor here. Very simple device. Okay. So when I say simulations, I mean we're doing that digital twin. We're going to take what I saw as a real component, that blue cylindrical looking things with those slots in it, right? Triangular slots in it. And I'm going to create the geometry model of it. And I'll change maybe the number of, slots that I have in there, the number of poles that I have in there, how, the wire that's inside those, the windings that are inside the motor there. And I'm going to look at it electrically. And I was saying, well, I could look at it electromagnetically because I got to look at the electric field and go look at the magnetic fields. They're two different, even though they're electromagnetics, the electric field and the magnetic field may have additional special equations that we need to use. Yes, we have Maxwell's equations, but what if we used a very specialized magnet? What if we used a different kind of material that I really need to have more advanced solvers for, right? I can't just use the canonical equations that I just learned from my textbooks. I'll pull for a advanced solver to be used in my software tool or my simulation tool that's creating geometry. So I have to mix material science and the mechanical drawing of the tool. And then maybe I want to consider the outside temperature. Maybe I want to consider that vibration in the luggage cabin. Maybe I want to say there's no air or there may be air around it. And so I have to consider the operating platform that this device is going to work in. And I have to make sure that I couple all the answers or all the results from each of these simulations together. I have to make sure I have the results from one simulation, one physics simulation, feed into the other simulation. So how do you do that? Well, Ansys has a tool that can help you design the different type of motors, right? Here's that inside, that's the 2D cross section of that blue cylindrical looking thing. And I can decide, what type of motor I want. We do have a selection, and here's just a few of the selections. We could have the permanent magnets, an inductor motor, okay, synchronous. We could have DC permanent magnets, okay, single phase induction. We actually have a drop down of all or several different templates of electric motors. So you don't even need to know the equation. As a matter of fact, what I was going to do, and I almost forgot, was if I have here, this is the front end. Let me just show you that this is indeed the front end of the tool itself. Now, I'm not using equations. I need to know and read the results of it, but I don't have equations to create this geometry. And when I said, oh, we have templates, I can open up a template and I need to make a motor that's for the aerospace industry, or maybe just industrial, or just some machine. I can pick a category of an application. Then I can go and decide on what machine type. And then I can go over and, select one that's befitting of my application. And you can create your own custom template on this. Let me close this so I don't have results on these simulations already. So I can go here and create an electric motor real easily from using some software tool, from some simulation tools. Then I can even go and take a look. Well, oh, this one says, oh, what kind of slots? I was saying, why are they triangular? I could change it. And let me just redraw it so you see a change in this. These should update on the fly. Okay, so you can see I could change the way the slots look, right? I could change the number of slots. So maybe I want to, instead of 18 slots, I can make 12 slots. Right, so I'm designing on the fly here. I'm thinking, oh, okay, whether it's a physical fit or by the equations, I need this many number of poles here. Or, maybe, like I said, I have a different number of poles. I could change it inside the rotor here. And you could see a change here. So it's inside here on the rotor, it may be hard to see. So let me go change that to 12. And this, as I hit redraw, take a look on the inner green that you see on this side. So you see that the number of poles are changing. And this is a 2D cut. Maybe I want to look at the different orientation. So I can go ahead and take a look at it axially here. But what's really nice about this is I can take that 2D geometry because it's very symmetrical, and I can actually take a look at it and see how it looks. Okay, and I was playing with the stator and the rotor on this part, but I can also explode the view and see how it's manufactured. in parentheses, right? How it's manufactured, how I actually build this thing. Okay, so again, we're not using textbook equations. We're given a geometry, or we can select a geometry, or we can select from a template. And that's really powerful because all these simulation tools have to start somewhere. And even though like I said, I went to school for electrical engineering, never took a drafting course. I will call myself an electromechanical engineer because in my job, I need to know how to create geometry. And having the geometry created for you, like automatically without having a draftsman with you, is gold, right? We're looking at the physical geometry. Make sure that electrically it's drawn correctly. This may be a big part, and this is low frequencies. And for those of us in the audience who are more high frequency, and we're looking at printed circuit boards, maybe that via, whether it's filled or not, and maybe if that ground plane is placed, close to a signal trace, does it matter electrically? Yeah, it does. Well, you know what? Or maybe the manufacturer says you can't make the spacing between the signal trace and the ground plane, only 10 mils. You need at least 50 mil clearance. All right, so but if I'm not in charge of the mechanical drawing and the draftsman is, and he changes it without telling me, man, heck, electrically it makes a heck of a difference, that spacing between the ground plane and the signal trace. So things that mechanical engineers may not think of, or don't think that it will have an electrical effect, sometimes do, and depending on the application and the frequency. So we know that. So it's never isolating. So though that is like an operating condition, just like for the motor, right? Temperature. Well, and also board is the same thing. So we need to know, besides the textbook equations, how they're being actually used in in the scenario. Okay, so let me go back over here, pull this back out here so you could see the slides. I wanted to show you that interface because that is such a advantageous feature. And in the classes on electric motors, you want to know how fast is that part rotating, right? Because it's the interaction, or both parts are moving. Our stator and the rotors are moving, and it's that interaction of what's going on, and electrically how they're interacting with each other. So here in this trace, right, the colored part here is really showing you how are the currents, where are the currents, red being hot, and blue being cold. You could see that in this scenario, there is interaction when the rotor and the stator are in close contact with each other, that there is coupling of the fields here. They're not all blue, or they're not all yellow. So, and we want to know where the fields are. We can't see current moving, but in simulation, we can see where they are and what is coupling to what. That the most important thing is, what is coupling to what? I gave it a little bit of an indication on these windings. Let me see. Did this? So if you saw like inductor loops, maybe in your labs, one of the components were these inductors, and they have all these wiring loops around some core, and so you get to see the windings in your device. But what's even nicer is this tool will say, "Oh, this is for power. We don't have single phase. We have like 3-phase devices." Well, I sure can. If I can't see current, I sure as hell can't see current and phase. But in a simulation tool, you can. You could see which windings are which phase and where they're located. So I could say phase 1, you know, third or fourth winding. I could see phase 2 or phase 3. Electrically, these are nice, need to know type of results. And you can have your typical graphs here as well. Okay, so take a look at torque and forces. We could see field plots. We could see winding patterns. And these are just some of the results that you can see. Besides seeing that, you can delve deeper in and look at exactly what's happening inside the slot itself. Okay. Again, other plots that we could see are voltage plots. I put in this voltage. What am I seeing out on, this winding or the second winding? There's a lot, there could be hundreds of windings. You could see, and it's not the geometry, even though I said, oh yeah, we have all these templates here and I can draw geometry. Well, that's not the most important thing. Really, the simulation tool is not really, it's using the geometry as an outline to create a mesh. And, excuse me, and the mesh that I see, or the geometry that I'm looking at, is shown here. Excuse me. And so what I need to do is really look at what the solver is trying to mesh. And it better look like the geometry that I'm trying to solve. So I would want a curved geometry to look curved and not staircased. And the other thing that we want to look at is efficiency. So I can really make a really great motor, and it could put out so much power. But if it's putting out 10 kilowatts of power, 50% of that, that's not good, right? I don't want to waste it. So efficiency is how much power that I'm creating and generating and that I'm actually using, not losing. And so this plot here will show that wherever it's really red, wherever it's really red, that's exactly what I want to see. So part of our engineering application education is to say, how do I read this plot? So if this were torque and efficiency, and I could say, well, at this point here, I could go up to this speed, but it's maybe this efficient. So we can read these efficiency plots and say, oh, this device will work up to this speed, or will work well and will be efficient up to this speed. Or perhaps it's a different type of motor. This one is more efficient at the higher speeds. And there are some applications where you need actually the opposite. You want it to have more efficiency at the lower speeds. So depending on the application and looking at the device results, such as the efficiency map, we can tell if indeed it's a good engineered device. Okay, so that's one of the plots that we can show. So besides the efficiency plot, maybe I want to see the speed, the torque, the transients that are on this motor as it's rotating, and which phase, right? So I have a very specific geometry. I have at a specific temperature with these specific materials, and I'm doing a transient analysis. So I want to see the response of the field plots or the speed at these different time steps. And we can do that, and we can plot it and show it. So the real takeaway here is there are tools out there, simulation tools of digital twins of real product that we can use to help make these electric motors, these small electric motor devices where the technology or the birth or the equations were birthed almost 200 years ago, almost 2 centuries ago. The more efficient we have them, and obviously we can't have 100% efficiency, but the more efficient they are, the more things that can be electrified, the more things that we can make for smarter devices. Now, the other thing that, I said I was going to embrace was, Well, these learning resources, there are so many of them. And great question that was in the chat was, so where do I go to find the answers? Well, if you're looking to learn how to do simulation, and for example, if we look back at that electric motor that I was using, and I only went into one of our tools, which was Motor-CAD, which was, let me make this geometry and see what happens. But what if I worked at a company that was using special magnets, and I really wanted to tweak and tune in the magnetic field using the material? Well, then I would pull for a different tool. And we do have on our Ansys website a video module on how to use that tool in an electromagnetic brake application. Those are those, think of the EMB similar to the rotor and the stator, but those are the switches that open and closes those airplane doors. That's just one application for it. Okay, so there are resources just on the simulation tool. And it's the next question will be, I don't have that simulation tool. It costs too much money. But we do offer a student version, which is free for use of our tools. And that in this Ansys electronic desktop, when we say electronics, they could be for low frequency for electric motors. They can go for be high frequencies like the antennas in the millimeter range. They can also be, used with thermal. So if you want to look at the thermal profile, trying to allude to that with the electric bike. So did it get too hot? Well, let me put that motor into the Maxwell, Motor-CAD and or Maxwell, and throw it into Ice Pack, which is in this electronics desktop for you to use, and see if I happen to put the operating temperature higher, or if I had a component that got hot and put it in or close to the device, what would happen, and see the results there. So it's always, electronics is electromagnetics. Let me actually visualize and see where the current is, or see where the electric or the magnetic fields are. And so again, a free download, shamelessly plugging it, because I think when I went to school, they didn't have that. And so I'm looking at black and white diagrams and whether they're dotted lines or straight lines or, solid lines. Here you get a digital twin with results that are in color so that I can actually read it. So I can't say enough about it. I think that every student, before they go, they should have some field simulation tool that you can see what you can't see with the human eye. Anyway, besides the tool that we offer, we have a place where you can answer questions. I don't know all the answers, but if I had a form where I could go and ask, so I'm trying to plot the torque on this device, and I don't understand what that plot means. Can you please explain it? So it's an open forum, and so whether it's someone from Ansys or someone who uses the tool, they'll come in and answer your questions. So there is a forum that is available. Part of that EMB module is part of what we call our Ansys Innovation courses. So that's a whole set of modules to teach you, to learn our tools. And it's not limited to electronics. As you can see here, we have fluids, we have structures, and we have some STEM activities for grade schoolers, high schoolers, and grade schoolers. Also, we have on-site under learning. We all, because now, thank goodness that we're almost out of the pandemic, or I could almost safely say we're coming out of the pandemic. We did have a lot of courses online, and we did partner with Cornell. And so we have several of their courses online available through our Ansys channel. Schools, HKN teams, guess what? You can have Ansys sponsor you. There's a lot, we sponsor a lot of teams for car racing, but then it's not limited. You have the Formula Student, the Solar Challenge. These are just, for our EMAG folks. What about a CubeSat, a satellite challenge? There are many other, challenges and sponsorships that we can do. So maybe part of your next year's, ideas or activities where maybe we'll participate in some challenge or some student activities. And if you're using simulation tools, perhaps Ansys will sponsor that for you. So really, in summary, all I really wanted to say that we do use simulation in helping us help our customers design and create product that will keep, the earth healthy, right? Earth rest goes in line with our earth rescue and sustainability. It goes with the byline of IEEE, which is in the advancement of humanity, so that we have a safe, healthy environment to live in. So I wanted to use a application and a device to show you how we do it. And I'm glad that all the other sessions had almost, the same buzzwords, the digital twin, how we're going to simulate it, sensors. And again, all for in the industrial end revolution. It doesn't have to be in Industry 4.0. What are the challenges, the engineering technical challenges that we are facing today? And one of the biggest one is, green. Let us keep this earth healthy. Let us keep going forward. And one of the ways is through simulation. So with that, I thank you for listening. And I'm open for questions.
Hey, Charlotte, that was wonderful. Thanks so much. I think your point about sustainability, and really, although we will have fossil fuels, and I know some people say, well, we shouldn't have them. The reality is we will have them for a long time because we have energy needs. But how do we make it most efficient, most clean that we possibly can, so that we can, as we search for these alternatives, as we start to develop these other systems that might be able to replace it, which is kind of far down the road, we have what we need to power today and power that innovation today. So I think that's really an interesting point. Thank you so much for making it. And these simulation tools, I've always been fascinated with it. So Ansys, actually, if you read The Bridge, which is our magazine, which is on electromagnetic compatibility and wavelengths and all this kind of cool stuff this time. This issue that just came out, you can get it on the IEEE website, HKN website, or on the IEEE app. Ansys has a simulation of a car right on the cover, right? Really a cool picture. So, and more about that. So if you want to read The Bridge, I think Sylvia or Stacy, if you can put that in the chat so people can go over and see that and read more about all the different ways that you can use simulation tools and how interesting that all is. Fascinating stuff. So the other really cool thing, and we're so happy that Ansys is with us. We appreciate that. We appreciate your support of The Bridge. But you've got a lot of jobs open. You've got some recruiters here. You're over in the expo hall. If you didn't get there earlier, you can still go register interest. Tell us a little bit about what kinds of engineers you're looking for, what kind of jobs are open, what kind of skills you're looking for. Because I know I ask people what kinds of engineers they are with their study, power and renewable energy, engineering communications, microwave engineering, and non-destructive testing. Some interesting stuff. So tell us about what you're looking for at Ansys.
So Ansys is a very large company. Let me just say that. And we're in the business of simulation, not just electrical, there's mechanical and thermal, right? And so we need all the physics. And I was trying to state, you go to school for electrical, you could also be mechanical, right? So you could also do fluids. So we would, we have many job openings, and I am a technical manager, so for electronics products. So what I'm looking for would be someone, for my specific needs, is someone who not only has the technical knowledge, the understanding of how, the foundations of electromagnetics, because we're all about electromagnetics. Yes, we have circuit, but our main tools are based on electromagnetics. So it's more than just circuits, Well, I would need to make sure that they have those foundational studies. But that's not the limiting factor, right? Because we're engineers, and because we're HKN engineers, guess what? I know for sure that person is teachable. They don't have to know it. It just so happens that they went to a school that wasn't focused on electromagnetics. But you know what? They're an HKN. They're a top student. I know fundamentally they are teachable and they will learn it and understand it. So I'm okay with teaching, people who are just coming out of school. We had several people came to our expo, and some were software developers or wanted to be in the they're computer science and they want to be a software developer. And so, yes, if they're using the same language as our developers are, and we have, again, many products, many developers, and we have one base languages, but we also have other languages that we use. That is fine too, because it's the way you think. It's logically the way you think. We're tool or simulation tool agnostic. We're looking for potential. We're looking for, and this is a non-engineering skill, we're looking for an individual who could fit into our existing team with our existing team members.
Right. So, we talk about that a lot. We talk about that culture, the soft skills, and that interdisciplinary teams that we need to innovate. We're talking about a lot about that today, to innovate and to come up with the solutions and, kind of work on these huge challenges we have in our world today and how we're going to solve them through our profession.
Yep. That's I think a very key is personality. Do you communicate well? The one thing, when I first started out in engineering, I was like, oh, I don't want to look like the dumb person in the room, so I'm not going to ask a question. I'm just going to go home, write down the words, and then back then it was looking through all the textbooks that I would have and try to understand the concept. At this point, don't do that. If you don't understand it, but at least if you try to embrace it and understand it, okay, do that first. Don't just go, oh, I don't understand. Please teach me and help me learn it. No, take, a little bit of sweat, go ahead and ask a question. Mm-hmm. You don't have to know the answers to everything. And yet you can't. I'm still learning. Decades in this industry, and I'm still learning stuff that's going on. So never hesitate to ask a question.
I think that's what's exciting. So in EDICAP particularly, as we have a great community of people that are very accomplished in their fields and as they network with each other. And in IEEE, what technical society do you belong to, Charlotte?
I belong to a few societies. So, my main one that I started out from school with was the MTT, which is the Microwave Theory and Technique Society. So I'm heavily involved with them, as well as the APS, which is the Antenna Propagation Society. So if anyone out there is going to IMS for MTT, or they're going to APS ERSI for the APS Society, I'll be out at both of those conferences. So make sure you stop by the Ansys booth to say hello. Right. So those are the two societies that I do support. But I'm also heavily involved with women in engineering, because, there's not a lot of us. And so just to make sure that we have an affinity group and there's some camaraderie, I support the Women in Engineering initiative.
Yeah, I think that's so important. And again, it just talks to the power of association, right? And the power of, professionals belong to a professional organization. So why this is critical, not only as a student, and again, we love to induct EDICAP students and celebrate all their hard work and really that character, attitude, and scholarship. But then how do we help people grow in their profession? And I think it's through sessions like this, through when we get together as EDICAP or as IEEE, and through our technical society. So I think that's a really important message.
Yeah, I think that, like I said, you can't know everything. And being part of the technical society, going to a conference, you know what, when I first started out and I was going to the conferences, I met the author of, one of the, what they call the Antenna Bible, right? Konstantin Balanis. And I'm sitting right next to him, talking to him. It's like the greatest, if I had my, antenna book with me, I would have asked them to autograph it right there. I mean, what are the chances of that? So it's good to be involved.
I know it's hard not to geek out because again, when I've met Vin Cerf several times and he's at a Kapanu. And when I wrote to him, he goes, "Yeah, sure, Nancy. Of course, I'd love to come and speak for Ed Kapanu." I'm always like, "Oh my God." Vin Cerf, Henry Savioli, Marty Cooper, I don't know, Erwin Jacobs. They're like, Bob Metcalf, sure. We'd love to be involved. It's meant so much to us. It's done so much for my career. Ed Kapanu has helped me so much, and IEEE's been an important part of what I've done through my profession. So again, you know it because really some of the biggest names, the people that really have identified or really level set things in our industries, here we are. We're all here together. So I think that's such a strong message. Well, Charlotte, thanks so much for this today. I know if people want to go over to your booth now, they can still register interest. We have something tomorrow called Power Hours, which is where we're going to have small group discussions. So if you really want to get more into in-depth discussions on different things, I know you're having a couple of interesting sessions or topical conversations that are going on during those power hours tomorrow afternoon. So that should be really fascinating. I hope you come back and talk to Ansys and all the experts over there with Charlotte. That'll be fun. And we have something called the Great Debate happening tomorrow. That's on Industry 4.0. We've got subject matter experts from around the different disciplines. So we want you to come back and spend some time with us tomorrow. The Great Debate, our power hours. Drop by the booth, talk to Ansys recruiters, see what kinds of opportunities are available for you. But thank you so much. We really appreciate you sharing your expertise and your time with us. And, I wanted to, like I said, can't thank you enough, Charlotte. Thanks everyone for attending.
No, thank you. Thank you for inviting me. I absolutely enjoy these sessions. And, anyone that has questions or interested in Ansys, feel free to reach out.
Mm-hmm. Yeah, they can get you in the People tab.
Yes.
You can reach out to anybody through the People tab, or if you're trying to reach out to Charlotte, you can always reach out to me. I'm Nancy Ostin. I'm the director of Ed Kapanu, info@hkn.org. I get to be connected to all these wonderful people. So and I get to work with the most talented, wonderful students there are. Don't I have the best job ever?
Yes, she does. I'm so envious. I want your job.
It is. It's the best job ever. Well, great. Thanks so much, Charlotte. We're going to close this session up for today, and we're going to see everybody tomorrow. Thanks for being with us here at the 2022 HKN experience.
Thank you, and I'll see you tomorrow. Thanks.